Welcome back to Chapter 8. This chapter is kind of like an introduction to Chapter 9, just getting us some review of some of the basic things. There will be some new stuff this chapter, definitely, but there's a lot of older stuff. For instance, this first section, we're looking at sequences. Sequences we've been looking at since Algebra 1. Possibly before. We have arithmetic and geometric sequences, but we'll also include limits of sequences, um, and whether or not sequences converge or diverge. So there will be some new stuff here, but it's based on a review of something that we've known for a number of years.
Is just a series of numbers. For instance, a sequence could be 1. Wow, this is how we're starting. Oh, there we go. My computer is all sorts of slow right now. So a sequence could be 1, 1/4, 1/9, 1/16, 1/25, etc. And the ellipses, those would be the 3 dots, tell us that it just keeps going. So now a sequence is kind of like a function. With a function, we would have, say, f of 1 equals 1, f of 2 equals 1/4, f of 3 equals 1/9, etc. With a sequence, we use a s with a subscript, which would be an index, telling us s1 equals 1, s2 equals 1/4, S3 equals 1/9, etc. And notice it's pretty much the same. One of the big differences between a function and a sequence is that these are the terms of the sequence. There's nothing in between. It's the first term, the second term, the third term. You're not going to have the 1.55 term. Whereas a function is going to be continuous. You can plug in any number for x you want. So with a sequence, the term, the number, which we generally use an n for instead of an x, but n is in the positive integers, or the natural numbers, 1, 2, 3, 4, 5, 6, etc. It won't be 0. You don't have a 0th term. You don't have negative terms. It's just that it starts with the first term and then just counts from there. So that's the big difference between a sequence and a function. We can find the equation for the nth term. A function, in this case, f of x would equal 1 over x squared. For a sequence, it would be Sn equals 1 over n squared. I mean, it's the same. In fact, this function that we're looking at is called the related function to the sequence. And a lot of what we're going to be doing with sequences, you can actually think about the function instead, because it gives that more continuous piece. When we write the names of a sequence, so this would be the nth term, Sn. If we wanted the sequence Sn, we would put it in squiggly brackets. Sn equals 1 over n squared in squiggly brackets. We can specify the domain if we wanted to. So this would be Sn from n equals 1 to infinity, which is what it is if you don't specify anything. But this means we could say Sn from 1 to 5. It means we wanted the first 5 terms. But this would go right over to here too. 1 over n squared, n equals 1 to infinity. So that's some sequence notation. One of the things that we see with sequences is whether or not it converges. Now, converging means that it's going to one number. It could be 0, it could be 3, it could be anything. As long as it's going to one number, it converges. If it doesn't go to one number, that means it diverges. Um, and that would be, it could be going to infinity. Like if we just had x squared, it's just going to get bigger and bigger and bigger going to infinity. Or it could not go to a number at all. Sine of x, cosine of x, those don't approach one number. And so if it approaches one number, it has a horizontal asymptote. And so you can find where it is by looking at the horizontal asymptote. The notation for convergence, we would have the limit as n goes to infinity of Sn, and it's going to equal some number, we'll call it k. We could replace the sequence with the related function to have the limit as n goes to infinity of f of x equals k. How do we find the limit as x goes to infinity? We could plug in infinity, see what happens. If we have, in this case, 1 over x squared, that's going to go to 0. If we had a fraction, how do we find the limit of a fraction? Possibly L'Hopital's rule. And so we know how to find the limit if it exists and there's a horizontal asymptote, it's convergent. If the limit doesn't exist, it's divergent. And if it is convergent, that means that there are a lot of other things that we can do with it. We have all sorts of properties with limits of converging sequences. So with these, both sequences Sn and Tn are convergent, and then C is a constant. So if we multiply the sequence by a constant, we're just going to multiply the limit by a constant. If we add or subtract two limits, we would add or subtract the actual, or the two sequences, we'd add or subtract the limits. So the one we were looking at had a limit of 0. If we added another sequence to it, in which case the first terms would add, the second terms would add, the third terms would add, etc., the limits would add. So if we had another sequence where the limit was 2, the limit of the sum would be 2, because 0 plus 2 is 2. Product property, multiplying two sequences. Again, we'd multiply the first terms, the second terms, the third terms, etc. We would multiply the limits to get where they go. Same thing with quotients, as long as the denominator doesn't equal 0, because bad news happens then. If we take the power of a limit, so we had, the one we were looking at was 1 over n squared. Well, that would be the same thing as the limit as n goes to infinity of 1 over n and squaring that limit. That's what the power property says. So if we know the limit of 1 over n is 0, then if we square it, that's still 0. And then the root property is the same thing as the power property, except with the root. And the inside has to be positive if the root is even, just because that's how roots work. And for both of these, the p has to be at least 2. If the p is 1, then that's not really an exponent or a root. And if the p is negative, weird stuff happens with roots of negatives. And when you have a power of a negative, you get 1 over that, which changes things significantly. So they have to be positive and bigger than 2. So that's a bunch of properties. You'll be using those, just splitting up limits. And we've worked with properties like this before. The questions will be similar. And finally, a specific type of sequence that we'll be looking at is a geometric sequence. A geometric sequence is of the form S of n equals r to the n. That makes a geometric sequence. Each time we're going to be multiplying by the same number to get from one to the next. You may recognize that as a function. This is going to be an exponential function. So the related function will just be exponential. It's a fairly specific kind. This will converge if r is in between -1 and +1. It will converge to be 0. The limit as n goes to infinity of Sn equals 0 every time. Technically, it converges if r equals 1, the limit as n goes to infinity of S of n equals 1, because if r equals 1, that's just going to be 1, 1, 1, 1, 1. It's like the most boring sequence on the planet. But technically, it does converge to 1. And then it diverges otherwise. So it can converge to 2 different things, or it diverges. And this is really as far into sequences as we're going today. We will continue to look at these. We'll look at series as well in the next section. And we'll be doing all sorts of stuff. So until then, keep working problems, keep asking questions, and as always, happy mathing.